Section 1.5, Infinite Limits. In 1.5, we're going to learn about behavior of graphs of a function and how to describe unbounded condition of a function. So consider f of x equal 1 over x that you see on the screen. This is a very famous parent function that you learned from algebra class. And as x approaches to 0 from the left, what is going on with your function value? So simply look at it. If you plug x equal negative 0.1, you get 1 over negative 0.1 and your y value become negative 10. If you plug x equal negative 0.01, I get 1 over negative 0.01 and I get negative 100. Let's plug a smaller value of x. When you plug x equal negative 0.001, your y value become negative 1000. And you can see the pattern now. So as x approaches 0 from left, your function value are getting very, very smaller without bound. It is going to negative infinity, as you can see. And we are going to use the notation here as x approaches to 0 from the left, and we will literally put the 0. 1 over 0 does not exist, but we're gonna put 0 from the left, and you can think of a very, very small value of left-hand side of 0, like negative 0.0000001 or something like that. And you can see this value will go to negative infinity because value will decrease without bound. Similarly, now let's look at the right hand side of 0. So as x approaches 0 from the right, your function value is increasing without bound. And we can also see numerically by plugging x values that are positive small numbers. So if you plug x equal 0.1, 1 over 0.1 gives you positive 10. When you plug x equal 0.01, 1 over 0.01 will give you 100. When you plug x equal 0.001, 1 over 0.001 will give you y value 1000. So we can also see as x approaches 0 from the right, your y value increase without bound and it will become positive infinity. So we are going to say x approaches to 0 from the right. 1 over x will be look like 1 over 0 from the right. So you know you're plugging positive small number that is getting closer to 0. And you can see this will create function value to be positive infinity. And these symbols are just symbols, but they are not real numbers. So strictly speaking, in this case, limit does not exist. They are just symbols convenient for us to describe unbounded conditions more concisely. And we're going to use that to only designate infinite limits. But like I said, don't forget that in any cases, limit does not exist. But when they just say find the infinite limits, you are going to use a positive infinity symbol or negative infinity symbol to just letting me know or letting readers know where function is trying to reach. You're only describing the behavior of a function, just one-sided limit of unbounded behavior. Now, let's consider fx equal negative 1 over x graph. And of course, as you can see, if you plug x equal negative 0.1, I have now negative 1 over negative 0.1. So that will make it positive 10. Likewise, when you plug x equal negative 0.01, you get 100. You plug x equal negative 0.001, you get y value 1000. So as x approaches 0 from the left, double negative will create positive large values of y. So y increase without bound, so it will go to positive infinity. So we can say that x approaches to 0 from the left, negative 1 over x approaches to negative 1 over 0 from the left, it actually goes to positive infinity. And if x approaches 0 from the right, you plug 0.1, you get negative 10, because now this time you will get negative 1 over 0.1. So this is actually negative 10. So when you plug x equal 0.01, you get negative 100. When you plug x equal 0.001, you get y value negative 1000. If x approaches 0 from right, your function value actually decreases without bound, which creates your function to reach to negative infinity. As x approaches to 0 from the right, negative 1 over x will go to negative 1 over 0 from the positive values that are very, very small, which will create negative infinity. So as we have seen so far, and if you had to evaluate limit x approaches to 0 from the left, you can simply think of 1 over 0 from the left, 1 over negative 0.00001, and that will give you negative infinity. If you have a limit x approaches to 0 from the right, 1 over x, it will be 1 over 0 from the right, like 1 over 0.00001. So this will go to positive infinity. If you have a limit x approaches to 0 from the left of negative 1 over x, you can look at this and say, oh, I have a negative number over 0.00001. So you will get positive infinity here. This will be limit x approaches to 0 from the positive, negative 1 over x will go to negative 1 over 0 from the positive. So you can think of negative 1 over 0.00001. That's gonna go to negative infinity. Evaluate each limit from the graph. Limit x approaches to negative 2 from the left. Negative 2 from the left, your function is reaching to positive infinity. Just read the graph. As x approaches to negative 2 from the right, your function is trying to reach to negative infinity. However, limit x approaches to negative 2 of g of x. What is the limit, guys? Well, limit does not exist. Now, here, when you got x approaches to negative 2 from the left of g of x is positive infinity, then that is enough for you to conclude that this limit x approaches to negative 2 of g of x does not exist. You don't have to compare left limit with the right limit, because if a one-sided limit is infinity or negative infinity, then actual limit as x approaches to c of that function value does not exist. Let's keep going. What is x approaches 1 from the left of g of x? From the left, my function is try to reach positive infinity. How about as x approaches 1 from the right? 1 from the right, my function again try to reach positive infinity. So limit x approaches to 1 of g of x does not exist. So that gives us calculus definition of vertical asymptote. The line x equals c is a vertical asymptote of f of x. Either of these limits occurs. Limit x approaches c from the left of f of x equal positive infinity or negative infinity, or limit x approaches c from the right of f of x equal positive infinity or negative infinity. Note that it says or. You don't have to find out left limit and the right limit of f of x. If a one-sided limit is positive infinity or negative infinity, then you can conclude x equals c is a vertical asymptote of f of x. So on the test, if I say find the vertical asymptote of a function, and if I give you a function, that's what you have to show, because this is a calculus class. In algebra class, you have learned you have a vertical asymptote of a rational function if f of c is not equal to 0 and f of c equals 0. Then x equals c is vertical asymptote. That's how you learned in algebra class. But now we have a calculus definition of a vertical asymptote. As you've seen previous page, if x approaches to c from the left of a function is positive infinity, we can clearly see there is a vertical asymptote there, right? And one-sided limit is enough to say there is a vertical asymptote there. So make sure you say the line x equals c, that's the number that x is trying to approach it to. The line x equals c is a vertical asymptote of f of x if one of these four limits occurs. Either x approaches c from the left of fx equal positive infinity, or that is negative infinity, or x approaches c from the right of f of x equal positive infinity or negative infinity. Either of all these four, you can conclude x equals c is a vertical asymptote of f of x. So let's do an example. Prove any vertical asymptotes or removable discontinuities using calculus. So we know now when we get vertical asymptotes, right? If we can prove that one side the limit as x approaches to particular number is infinity or negative infinity, then x equal that number where x was approaching to is a vertical asymptote. Now, do you recall when do we get removable discontinuity? We have a removable discontinuity at x equals c if f of c does not exist but limit x approaches c of f of x exists. Alright, so let's do the following problem. I have a rational function g of x equal 2x squared minus 7x minus 4 over x squared minus 16. So let's go ahead and factor 2x plus 1 times x minus 4 over x plus 4 times x minus 4. So I can see that g of x does not exist at x equal negative 4 and x equal 4. And clearly, if x is 4, you get 0 over 0, which you know there is a hole there. So first, at x equal negative 4, you can just see when you do the mental math, if x was negative 4, you get number on the numerator, but you get 0 on the denominator. From algebra class, you know you have a vertical asymptote there. However, when you show the work, you gotta show calculus work to prove it is vertical asymptote or it is removable discontinuity. So at x equal negative 4, we just said we're gonna get number over 0. So I'm gonna actually show one-sided limit. So limit x approaches negative 4 from the right of 2x plus 1 times x minus 4 over x plus 4, x minus 4. Well, these you can cancel, which is limit x approaches negative 4 from the right of 2x plus 1 over x plus 4, which is equal to, now if you plug negative 4 for x on the numerator, I just get negative 7. X now approaches negative 4 from the right, negative 4 plus 4 will get closer to 0, but because negative 4 is here, and this is where negative 3 is, so if you go from the right, this number will be a number close to negative 4 that's coming from the right. Negative 3.9999999. That's what the number is gonna look like. So when you add the 4 with it, you're actually gonna get positive number that is close to 0. So you have a negative number on the top and you have a very small positive number in the bottom, which will make this function to reach to negative infinity. Because one-sided limit is negative infinity, you know you have a vertical asymptote there, so you can conclude that you have a VA at x equal negative 4, and vertical asymptote name is x equal number, so your vertical asymptote will be x equal negative 4. Now, how about at x equal positive 4? At x equal positive 4, clearly g of 4 does not exist, right? Because that's gonna create 0 over 0. However, what is the limit x approaches to 4 of 2x plus 1 times x minus 4 over x plus 4 times x minus 4? Because this function is equal to this function at all x except x equal 4. I could actually find the limit from this function after it's cancelled to x plus 1 over x plus 4, which is equal to 9 over 8. Because g of 4 does not exist, but limit x approaches to 4 of g of x exists, this point is removable discontinuity. So you can say that you have removable discontinuity at x equal 4. Let's do one more question. Prove any VAs or removable discontinuities using calculus. Do you see? It says using calculus. F of x equal sine x over x squared minus 3x. We should start factoring first. So numerator is fine. It's just sine function. Denominator, I can take it out the x times x minus 3. So clearly, this function is not defined at 0 or 3. So let's take a look at first at x equals 0. At x equals 0, f of 0 is equal to sine of 0 over 0 times 0 minus 3. And sine 0 is 0 over 0. So this is undefined. And what we're trying to say is f of 0 does not exist. However, because you have a 0 over 0, but limit x approaches to 0 of sine x over x times x minus 3. Do you guys see something familiar? I have a limit x approaches to 0 of sine x over x. Yes? This is a special limit that we learned in section 1.3 about special limit, and you are supposed to memorize it by now. So we can split this as a product of two functions. So limit x approaches to 0 of sine x over x times limit x approaches to 0 of 1 over x minus 3. So this part, you guys know what is the special limit? It was 1 times. Now you can plug 0 here, and that will be 1 over 0 subtract 3, which is equal to 1 times negative 1/3, which is equal to negative 1/3. And because f of 0 does not exist, but limit x approaches to 0 of f of x exists, so thus f has a removable discontinuity at x equals 0. Now, let's look at x equal 3. And what is f of 3? F of 3 will be sine 3 over 3 times 3 minus 3. So I get sine 3 over 0. So sine 3, make sure you put it in radian mode. And sine 3 is actually a positive number. So you're going to have a vertical asymptote here because you have a number over 0. But we got to use calculus to show that you have a vertical asymptote here. So limit x approaches to 3 from the right of sine x over x times x minus 3. So 3 from the right, sine 3 is not 0, so you can just plug 3 there. And x is not 0, so you can just plug 3 there. But for this x minus 3, instead of 3, you are approaching to 3 to determine the sign of this infinite limit. You could think of x being as 3.0000001 or something like that. So it's gonna give you positive very small. And 3.0000001 minus 3 is 0.00001. Even if you multiply by 3, it's still 0.0000003. So when you have a number divided by that, it's still gonna go to infinity. So you're gonna get a positive infinity there. So you know that you have a vertical asymptote, and your vertical asymptote is x equal 3. So then what do we do if we have infinity plus number or negative infinity plus number? Or what happens if we do infinity times number, stuff like that? So here is the properties of infinite limits. And please only go by these rules and do not create rules. So you can only use the facts that we learned or properties that we learned to determine what the answer has to be. So properties of infinite limits. let C and L be real numbers and f and g be functions such that let's make a little more assumption here to make it more clear for everybody. So let's just say L is a real number that is greater than 0 and K is greater than 0 also, so that if you see negative K, it will mean the negative number. And then let's just say limit x approaches to c of f of x is infinity. Let's just say limit x approaches to the same number of g function gives us limit L. Limit x approaches to the same number of h function, let's say it gives you a limit also, but let's just say it's a negative number. Then what would happen if you have a limit x approaches to c of f of x plus g of x? Well, we have learned this before in the past. If we have a limit of sum of two functions that was equal to sum of limits of two functions, so that will be equal to limit x approaches to c of f of x plus limit x approaches c of g of x. And by given, limit x approaches to c of fx is infinity plus limit x approaches to c of g of x is a positive number L. So what do you think, guys? If you have an infinity and you add some positive number with it, what's gonna be the result? Of course, this will still go to positive infinity. Now, what would happen if x approaches c of fx times gx? We also learned that limit of a product of two functions is equal to limits of two functions. So limit x approaches c of f of x times limit x approaches to c of g of x, which is equal to, well, first limit is a positive infinity and the second limit is given to be L, and L is a positive number. So if you multiply infinity by positive number, of course the result will give you positive infinity. Likewise, if I multiply two functions but limit h goes to negative number, then limit x approaches to c of fx times hx is equal to limit x approaches to c of f of x times limit x approaches to c of h of x, and that will be positive infinity times negative k. And because you multiply the positive by negative, result is going to be negative infinity. How about limit x approaches to c of g of x over f of x? This is equal to limit x approaches c of g of x over limit x approaches to c of f of x, provided that limit x approaches to c of fx is not equal to 0. And limit of g of x as x approaches c is L, and limit x approaches to c of f of x is infinity. So you can think of 1 over 10, 1 over 100, 1 over 1000, 1 over 10,000. So where is this quotient gonna go? It's gonna get closer to 0. Now let's use those properties to evaluate each limit. First one, limit x approaches to from the right of 1 over 2 minus x. So if you come from x to from the right, number's gotta be bigger than 2. So you could think of x to be 2.00000001, something like that. So then you will get 1 over, to subtract 2.000001 will be number close to 0, that is negative. So when you have 1 over negative zeros, we said it's gonna go to negative infinity. How about limit x approaches to 1 from the left of x plus 1 over x squared minus 5 times x minus 1. So that will go to 1 plus 1 over 1 squared minus 5 over here. I need to plug number that is close to 1, and this time I'm coming from the left. So what is the number close to 1 that is coming from the left? Good candidate will be 0.999999999. then you will have 2 on the numerator. 1 squared minus 5 is negative 4. And then 0.99999 minus 1 is positive number or negative number. It's gonna be negative number very close to 0. And because it's a negative number very close to 0, when you multiply by negative 4, it's gonna become positive number that is very, very close to 0. So this is what you're gonna get. Since it's a 2 over number that is close to 0, but it's a positive number, it is going to go to positive infinity. Third one, what would it be limit x approaches negative 2 from the left of negative 3 plus 5 over x plus 2 square. This is a sum of two functions. So I can split this limit. This is limit x approaches negative 2 from the left of negative 3 constant function plus limit x approaches negative 2 from the left of 5 over x plus 2 square. And limit of a constant is a constant. So limit of negative 3 as x approaches to negative 2 is still negative 3. And now for the second one, I will actually plug in number that is close to negative 2 that is coming from the left. And here's the negative 1 and here's negative 3. So if you come from the left, number very close to negative 2 from the left will be negative 2.000000001, something like that. So that will actually give you negative value. So I'm gonna have 5 over number very close to 0 that is negative number, but you are going to square that. So you have a negative 3 plus 5 over a number that is very close to 0 that is positive, and this will go to negative 3 plus infinity. And when you have infinity, even if you add with the negative 3, it's gonna still go to infinity. Let's keep going. Evaluate each limit. Limit x approaches negative 1 from the right of x times x plus 2 over x plus 1 equals limit x approaches negative 1 from the right of x times limit x approaches negative 1 from the right of x plus 2 over x plus 1. So first one, I could just plug negative 1 there. So it is negative 1 times. And when I plug negative 1 on the numerator, I will get negative 1 plus 2. However, for the bottom, negative 1 from the right, and this is where the 0 is, and this is where negative 2 is. So x goes to negative 1 from the right. What is the number very close to negative 1 would be? That would be negative 0.999999999. And then if you add 1 with it, you're gonna get number very close to 0 that is positive. I have negative 1 times 1 over a number very close to 0, 1 over positive very small number close to 0. So I have negative 1 times infinity, so it will actually go to negative infinity. Let's do the second problem. Limit x approaches pi from the right of 3 plus 2 cosine x over sine x will go to 3 plus 2 cosine pi over sine of pi is 0. So I need to verify what the value would be if x approaches pi from the right. So this is a sine graph looks like, if you recall, from 0 to pi. So this will be pi, and x is approaching to pi from the right. So x is approaching to pi from the right. Your values are getting closer to 0, but they are negative numbers. So you are gonna get a negative number that is very close to 0. And cosine of pi is, graph looks like this, right? So at pi, this is from 0 to 2 pi. At pi, it is negative 1. So that will be 3 plus 2 times negative 1 over a negative number very close to 0, which is equal to 3 minus 2, which is 1 over negative number very close to 0. And therefore, this will go to negative infinity as well. Let's do the last problem. limit x approaches pi over 2 from the left of x plus pi over cosine x is equal to pi over 2 plus pi, and as x approaches pi over 2 from the left, this is pi, so this is pi over 2, and if x approaches pi over 2 from the left, you can see graph is above x-axis, which is all positive value. So it will eventually get closer to 0, but it will be a positive number. So that will be, so positive number very close to 0. So you have a pi over 2 plus pi gives you 3 pi over 2 over a positive very small number, which gives you positive infinity. Thank you guys. This is all for section 1.5. Happy studying.